Welcome to Module 25 in this series of short lectures on statistical quality assurance and statistical process improvement. We're beginning to discuss Shewhart control charting, statistical process control or statistical process monitoring. And in Module 24, introduce some of the basic ideas and goals of control charting. We're going to carry on with that general introduction in Module 25, but try to make things a bit more concrete by doing showing some calculations. Then in subsequent modules, we will discuss specific kinds of Shewhart control charts and give details in their use and operation. But let's talk about an example. This is an example that's used regularly in IE 361 classes at Iowa State University. It's an example where a process with mean 5 and standard deviation 1.715 is used to create samples of n equal to 5 individuals. The specifics happen to be that there's a bag of washers, and on those washers are written numbers. Those numbers have mean 5, standard deviation 1.715, and as a class demonstration, collections of 5 washers are drawn and their averages and ranges are recorded. We want to talk specifically for a bit about doing control charting for averages for X bars and control limits for X bar, knowing the nature of the bag, knowing the nature of the process or the population, are to take a mean of 5 and add or subtract 3 standard deviations of X bar. And the standard deviation of X bar is the process standard deviation over the square root of the sample size. That produces an upper control limit of 7.3 and a lower control limit of 2.7. And the notion is that any X bar that is between those values is plausible as coming from the quote-unquote brown bag process. Any X bar that is outside of those limits indicates that something else is going on. Here we have a series of 15 X bars that were collected in class in one of these demonstrations. The truth is that during that demonstration, only the first 12 samples actually came from the brown bag, but sample 13, 14, and 15 came from a different process, from a different population. If one looks at the first 12 of those X bars, they all fall inside of these standards given control limits here. 7.3 is an upper control limit, 2.7 is a lower control limit. None of those first 12 X bars are unusual in comparison to those control limits, but beginning at sample 13, we get X bars that plot outside of control limits. This is an example where the data tell us that indeed something is different beginning at sample 13 than the standard. That it's just implausible that those last 3 X bars came from the brown bag, and indeed physically they did not. There's a reasonable question that then arises: what if one wants to do not standards given control charting. Suppose that one didn't know what the standard or what the ideal brown bag process was, but had only these values to work with. What if one wanted to do retrospective charting? Well, one thing that one could do would be to say, I have there 15 X bars and I have 15 ranges. Those 15 X bars could be averaged as a provisional estimate of a process mean, saying, well, if there was no instability, no change across the 15 samples, those 15 X bars would all be representing the same process mean, and similarly, those 15 ranges would be representing the same process spread or process standard deviation. So if one averages 15 X bars, one gets 6.08. And that's a plausible estimate of process mean if one says, well, provisionally, let's just calculate as if all 15 of those samples came from the same process. 6.08 is about the best one can do for estimating a process mean. That's the average of X bars, so we'll call it X bar bar. Further, if one wanted to process ranges into some kind of an estimate of process standard deviation, we've already seen in the context of gauge R&R that ranges are not on the same scale really as standard deviations, and one has to do some kind of conversion of range to an estimate of a standard deviation by doing division by little d2 being based on a quote-unquote sample size being the number of data points that actually go into the computation of any single range. So back in this data set, every one of those 15 ranges came from 5 values, came from a sample of size 5. And so it's not 15, which is the number of samples, but rather it is 5, which is the number of values used to compute each range that is needed to find this control chart constant little d2. If one looks in a standard table of control charts, little d2 for a sample of size 5 is 2.326. If one takes 15 ranges, adds them up, divides by 15, one gets R bar, that is an average range, and the ratio of R bar to little d2 is 2.092, and that is about the best one could do without knowing what the brown bag was really like, without knowing what the standard process was really like in terms of making an estimate of process standard deviation. If one employs this 2.092 and 6.08 as provisional estimates of process parameters and plugs them into standards given control limits, there's the 6.08, there's the 2.092 in place of 5 and 1.715, which are the truth about the brown bag process, producing somewhat different control limits for as-passed data or retrospective control limits than one has with standards given limits, but then one is not using or feeding in the unknown values or the values of process parameters in this set of calculations. One then takes these and applies them to the X bars and has a way of asking, well, is there any set of process parameters that really is consistent with that set of X bars? And as one looks across those 15 X bars, one finds that at samples 14 and 15, X bars are not inside these retrospective control limits. And so even without knowing the values of the brown bag process parameters, one can operate retrospectively and come to the conclusion that these averages and ranges are not consistent with a picture of the data generating mechanism as being stable across this entire period of data collection. There has to have been some kind of process change basically in that period of data collection. There are a couple of more concepts that we need to discuss before getting to much more specific technical calculations with control charts. The first of these is the notion of rational subgrouping. When one takes data from a particular time period and processes it to make a plotted statistic, something like an X bar or an S, one is essentially assuming that during the period in which the data were collected that are processed into that plotted statistic, that the process was physically stable. That is, one is using a model that says data processed to make X bar or R or some other plotted value are random draws from a fixed distribution. That's what one really has to have in order to do sensible, to make reasonable use of a control chart. If that's not plausible, then one has no business processing those data into a single X bar or a single R. In some contexts, it's perfectly reasonable to take several items during a time period and say these should adequately represent the entire time period. On the other hand, in extremely low volume contexts, it may be that the only natural sample size is a 1, and that there really is no way to do rational subgrouping. We'll in a few modules have something to say about how to do control charting based on sample size 1. But the point here is if you're going to process data to make a plotted statistic, you are essentially saying those data all represent the same fixed set of physical conditions. A second set of ideas, or a second point that we need to make at this juncture, is that there's a persistent confusion with people that make use of control charts, confusing the notion of control limits with specifications. These are really much different ideas. and it's very important that users keep these ideas separate. Control limits are used in SPC on Shewhart charts basically to assess process stability. They apply to something like an X bar or an R. They usually derive from process data. That's different from the notion of a specification. The specification on a widget diameter has to do with whether or not that diameter is acceptable, whether a diameter of a particular size is workable. Specifications apply not to plotted values, but to individual measurements or individual values. And they're not derived typically from process data, but rather from performance requirements. It's perfectly possible that a process is stable and yet does not produce acceptable individuals. It's perfectly possible that a process produces acceptable individuals, produces individuals meeting specifications, but is not stable in the sense of staying inside of rational control limits. Control limits, SPC, indirectly deal with making a process behave well, but they are not directly concerned with process acceptability. They have to do with process stability. The in-class example that's always used at Iowa State is that in addition to making these averages and ranges, individual items individual numbers are looked at and compared to specifications of 3 to 7, and measurements that are outside the range 3 to 7 are called defective or out of specifications, not functional. The point that's made during class is that comparison to 3 to 7 has nothing to do with whether or not the brown bag process is operating. That is, whether the process is stable at given standards or not. The fact that they're for the mean of 5 and a standard deviation of 1.715, there's about 75% of the values in the population that are in specifications. It really has nothing to do with whether or not X bars and R's are inside control limits. We try to make the point that specifications are not control limits. Control limits are not specifications. What finally this needs to be said here as a final point is that control charting can signal the need for process intervention. It can keep one from tweaking a process that is operating in a stable fashion. Those activities can aid in reduction of process variation, but all that one is really doing when using process monitoring SPC is to reduce variation to the minimum possible for a given system configuration. bringing a process to stability. That can provide a background for subsequent process improvement that is aimed at order of magnitude improvements in production methods, for example. But SPC is not directly, doesn't provide direct guidance in that. It provides guidance in assessing whether a process is physically stable as presently configured.